So now we want to get into how exactly do we approximate the area underneath the curve. So this is kind of similar to how we would approximate the rate of change by finding 2 points. If we want to approximate the instantaneous rate of change, we would find 2 points that are very close together, and we would find the average rate of change between them. So same kind of idea here. So let's just say, that this is our x and our y, and we'll just keep it general for now. We won't give names to these functions or anything, but let's just say we have some kind of line segment like this, or curve segment, I guess you could call it, like this, where we're cutting off the points at, say, A and B. Okay. So we'll call this curve F. Okay. So the area underneath of it, right, which should be basically this region right here. Okay, so we'll call that A. Okay, for area, A. So we want to find A. Okay, so first we just want to look at how we would approximate A rather than actually find A. So again, the idea with this is that the simplest way to do it, at least, is to find rectangles and just find a bunch of rectangles basically, and find the areas of those rectangles, and that'll give us some kind of approximation for that area underneath that curve. So there's different ways we can do this. We're working on the interval A to B with the endpoints included, right? So if we want equal subintervals, right? In other words, if we want to divide this up into rectangles, and we want all of those rectangles to have the same width, then we want to divide this interval into equal subintervals. So say we divide it into n subintervals. So if we do that, if we divide it into n equal subintervals, then the widths of all of those subintervals will be b minus a divided by n. Okay. So just to see an example with real numbers, like if we were doing 0 to 1, for example, and we wanted to divide it into 5 subintervals, okay, then these subintervals would have width 1 minus 0 divided by 5. Right, so 1/5. So then the actual subintervals themselves would be 0 to 1/5, 1/5 to 2/5, right, 2/5 to 3/5, 3/5 to 4/5, and 4/5 to 5/5, or just 1. Okay. So this is kind of what we mean. So this is like the idea of what we mean. Okay. So we can do this we can basically take any interval and we can divide it into n equal subintervals, and we can divide it into non-equal subintervals as well, right? So we would call this, this example right here, we call this a partition of 0, 1. And of course, there are infinitely many partitions that we could make. We could do 4 subintervals, 3 subintervals. And because they're of equal width, in this case, we call it a regular partition. Okay. So again, you don't need to make them the same width, right? You could, if there's one area that's relatively flat, right? Maybe you make that just one big rectangle, no need to divide it up. Maybe it's completely flat, a constant function, then there's no reason to divide it up, right? So you just use a big rectangle right there. And then on the curvier parts, you would, maybe divide it up a little more finely. So this one would be a regular partition, again, because it's equal width. And that is generally the way we're going to look at these, is by dividing it into rectangles of equal width. So the two basic ways that we could go about actually forming the rectangles are by using the left endpoint to make our rectangles of each subinterval, or the right endpoint of each subinterval. So we call this the left one, for example, we call a left endpoint approximation, or a left-hand sum. Okay, so we might call this a left endpoint approximation. Okay. So in general, when we take these rectangles and we add them together to approximate the area, they're called Riemann sums. So we might also call these left Riemann sums. Okay. The book I'm looking at just kind of, it introduces this Riemann word a little bit later, so I'll write that down as a definition after we look at a couple of these. But Riemann, he was one of the, a very prominent mathematician that kind of came up with, not this idea of integration, but a specific type of integration. There's actually a lot of different types of integration. So we're looking at one particular type. But anyway, so if we imagine it on this curve, what would we mean by a left endpoint approximation? Okay. Well, what we would do is we would say, okay, let's just say we divide A to B into 3 subintervals. Okay, so maybe we would divide it up like right here, for example, right? And let's just give these other names, like maybe we call A, usually we call the first one like x0. So maybe we say x0, x1, x2, and x3. So now we have these 3 subintervals of equal width, right? And they all have width b minus a over n once again. So what we do is we say, okay, let's take the left endpoint, and whatever f value that corresponds to, we'll take that as the height of the first rectangle. Okay, so maybe I'll use a different color here to kind of make this stand out a little better. Okay, so we take this as the height, and then that's the height for this entire rectangle. So going over to the next endpoint. Okay, so the width here is b minus a over n. The height is f of x0. Okay, whatever x sub 0, the f point is at that point. So with this one, we're greatly overestimating the area, right? So we might overestimate, we might underestimate. There's, some kind of trade-off that has to be made here. So then to continue doing it with the left endpoint, we then would go to x1 as for the next rectangle, and we would take that height to be the height of the next rectangle. Okay. So again, it has the height b minus a over n, but now, or the width rather, but now the height is f of x1. Okay. And then finally, we do the same thing with x2. So this is the height right here, and we bring that over here. And now the height is f of x2, and the width is again b minus a over n. Okay. So we would approximate the area here, A, as b minus a over n, and then this is going to be times f of x0 plus f of x1 plus f of x2. Okay. And we actually don't need to write n every time. We could have just written 3, I guess, because we actually defined what n is, right? Because it was 3 subintervals. So they're all multiplied by the same width, so we can just kind of pull the width out to the front here. So using the sigma notation, this would be b minus a over 3 times the sum of f of x I minus 1 of I equals 1, 2, 3. Okay. So generally we say that the subinterval it goes from xi minus 1 to xi. Okay. So the left endpoint of it is xi minus 1. So that's why I wrote xi minus 1 here for the argument of the function. Okay. So with this idea, you can kind of get how we would generalize this. The only thing we did really was write 3 in for n. So if I just change that to an n, then we have a general formula for as many rectangles as we want of equal width, right? So a left endpoint approximation would be I equals 1 to n of f of xi minus 1 times delta x, where delta x is the width of each rectangle. Okay, so this delta, it's like a little triangle. It's like an alternative way to write the Greek letter delta. There's also like the little d looking character, right? And we'll see that in different contexts. But so we only write delta x here instead of the b minus a over n because in general, maybe we're not defining it over an interval. Maybe we're defining it over the entire function or something like that, right? So in general, we say the area is approximately equal to what we call Ln, which stands for the left sum. So it's important to be careful because sometimes we also talk about the lower sum. So, and we'll talk about that later. So it's important to know which one it is in context here. But this would be f of x sub 0 times delta x plus f of x 1 times delta x, all the way up to f of xn minus 1 times delta x. Okay. So if we want to do this, in an actual function now, let's look at how we would do it. So let's look at x squared. Okay. So we'll just look at, again, from 0 to 3. So I'll just draw the right side of it. So first of all, it's important to know, if we're looking at those points, what are those points? So this is x squared. So we'll say the y is 0, y is 1, 4, and 9. Okay, and we're not going to need the last one because we're doing the left endpoints, but it'll be helpful for when we do the right endpoints. So let's just draw the points on here. So this is 1, 1, let's say. Okay, this is 2, we just have to kind of use our imagination for the scale here. I'll draw this a little bit larger to make it a little bit easier. Whoops. Okay, so we'll say, what's that, right? So we'll say that's 9, that's 4, that's 1, that's 1, that's 2, that's 3. Okay, so for the left endpoint approximation here, if we divide this into 3 subintervals, because that would be convenient, right? Because that would just be between 0 and 1, between 1 and 2, and between 2 and 3. Right, so we do 3 subintervals. Okay. Then that means that the width of the subintervals is 3 minus 0 over 3, which is going to be 1. Okay. And then we take the left endpoint for the heights of the rectangle. So the left endpoint here is 0. So the first one has height 0. So that's easy enough, right? The second one now has height 1. And we bring that over, and this is our second rectangle. Okay. The second one has height 4, or the third one rather. And that's our third rectangle, and then we're done. Okay. So we've clearly missed a lot here, right? We have a lot of open space here, namely this part and this part and this part. So we're definitely vastly underestimating it. But you know, this is one way to get somewhat of an approximation here. But it's just important to keep in mind that it is an approximation. So what this would be then, ln, specifically L3, because we're doing 3 subintervals, is that it would be 0 times 1, so the height times the width, plus 1 times 1, the second height times the width, plus 4 times 1. Okay, so you don't have to write the times 1 on each part. You could just write it like this. So that's just the distributive property, right? But regardless, we get 5. Okay. Now, if we want this to be maybe a bit of a better approximation, what we could do is we could divide it into more rectangles, right? So we could make these smaller rectangles. So maybe we do 6 subintervals. Okay, so I'll do this one in purple here. And for that, maybe we need some more X and Y points as well. First of all, the width of the rectangles here will be 3 minus 0 over 6, so it'll be 1/2. So we're going to need every half point. So we already have the full point, so now we're going to need 1/2, which is going to be 1/4. And you can use decimals if you're more comfortable with that. 1.5, which is 3 halves. The output will be 9/4. 2.5, which is 5 halves. The output will be 25/4. Okay. And then that's all we'll need if we need the left endpoint approximations. So I'll kind of put some tick marks here at the halfway point so it's easier to keep track of. So the first one still has height 0, right? But now the second one has height 1/4, which is what we found over here. Okay. Then the next one is the same as the last one, right? So that has height 1, but we only go half of the length. And then the next one has height 9/4. Okay. And then the next one is equivalent to the last one. It's height, right? But we only go half the length again. And then the next one, the height is 25/4. Okay. And you know, when you're finding these, you don't have to draw it every time. I'm just doing it to display it. Like you can usually just get by just doing the math, right? If you just if you just have the points, you don't really need the picture to actually compute the problems. But it's good to visualize it. So L6 is going to be, so I'll just write the width out on the end here, right? Because all of them have width of 1/2. So then the heights are going to be the left endpoint. So 0 plus 1/4 plus 1 plus 9/4 plus 4 plus 25/4. Okay. 1, 2, 3, 4, 5, 6. So then you can use a calculator for this if you want, or just convert everything to a fraction. Okay, 16/4. Okay, so 1 plus 4 is 5, plus 9 is 14, plus 16 is 30, plus 25 is 55. So 55/4 times a half is 55/8. Right? So this will be, what is that? A little bit less than 7, right? So I think 6 and 7/8 particularly, right? So it's more than our last approximation pretty significantly, but that shouldn't be too surprising because we cut down on the amount of white space here, the part that we're missing out on. So essentially the idea is if we keep making these subintervals smaller, then our approximation is going to get better and better. And if we take the limit as the subintervals, the number of subintervals goes to infinity, so the limit as n goes to infinity, then we would eventually end up with, or we would exactly end up with the exact area under the curve, right? And so that's kind of what we're working up to here. But so this is the left endpoint approximations, or the left Riemann sums.